Hi, today we're solving problem 38. In this problem, we're shown the number 192 and we multiply it by each of 1, 2, and 3. So we get 192 times 1, which is 192, 192 times 2, which is 384, and 192 times 3, 576. By concatenating all of these three products together, we get a 1 through 9 pan-digital. And so this number contains all of the digits 1 through 9 in some arranged order. And we can do the same by taking 9 and multiplying it by 1, 2, 3, 4, and 5, which gives us another pan-digital. We need to find the largest 1 to 9 pan-digital 9-digit number, which can be formed as the concatenated product of an integer with 1, 2, all the way to n, where n is greater than 1. So this problem is actually pretty simple. I mean, the first thing when I saw this problem, I went ahead and I'm like, 987654321. We can't do this, of course, because n has to be greater than 1. So let's try to find an upper bound for n when n is 2. When n is 2, we're going to take the number, multiply it by 1, multiplied by 2, and then put those together. And we know the number multiplied by 2 has to be at least the length of the number multiplied by 1, which is the number itself. So we can use this to find an upper bound based on the number of digits in the number we start out with. If we think about a number with 5 digits, we know that it can't work because you'll have 5 digits for your first number and at least 5 digits for your second number. And that will be 10, which is greater than 9, because we're looking for only a 1 to 9 pan-digital. But with 4, we still have possibilities in which it may work. So now we know that the maximum number, the base number, this 192, whatever number goes here, must be at most 9999, because that's the largest 4-digit number. From then, all we have to do is implement an algorithm to tell us if it's possible to produce a pan-digital number by multiplying your base by consecutive multiples, and if so, return that pan-digital so that we can find the maximum. So let's switch over to IntelliJ. I'm going to do def concatenated pan-digital. It's going to take a number of type int, which is our base. We're going to implement this as a tail recursive helper based method. So I'm going to create def helper. Since we're concatenating, it's going to be useful to keep track of the number we have so far as a string. So I'm going to have cur of type string, and this will be a number, but we can convert that at the end. And we also need to keep track of what's the next number we have to multiply our base by. So we're going to start out with 2 for cur multiple. So now how do we implement helper? The first thing we want to check is that cur doesn't have any duplicates, because a pan-digital number has no duplicates. So and we can do a quick check if it contains duplicates. What we can do is we can count the distinct characters in cur, get that length, and if it's not equal to the length of the original string, that means we have some duplicates. And then we return none. This is going to return an option of the string. So this can be either some or none. We return none if we can't find a pan-digital number, and we return some with the pan-digital number if we do. So here we have none. Otherwise, if... Now here we're going to detect if it is a 1 to 9 pan-digital. The first thing we need to check is the length is 9, And the second thing we need to check is that the lowest digit is 1, because 0 is not allowed in a 1 to 9 pan digital. So we need to do and cur.min, and we can just do a min on all of the characters, equals to 1. So 1 has to be the minimum. If it is, we have now found a pan digital. We can return an option sum with the current string. Otherwise, now we need to recurse. How do we recurse? Well, we're just going to call helper. We're going to take cur and we're going to concatenate it with our number multiplied by cur multiple. So plus num times cur multiple. And since we're working with a string, we need to do .toString on this multiple. So this gives us the new cur, and cur multiple, we just increment it. So cur multiple plus 1. And all we do when we're, to initialize this tail recursion, is cur is just going to be num.toString. So we start out with our number, and cur multiple is going to be 2. So we can actually println concatenated pan digital of this number. We can run this. And we get this number, which is this. So we know that our pan digital finder is correct. Now all we have to do is find the maximum pan digital of all base num values from 1 to 9999. So we're going to start with 1 and we're going to go to 9999. Now what I'm going to do is I'm going to do a flat map. I'm going to take the current number and I'm going to do concatenated pan digital with that number. So we're actually doing something really interesting here. We're doing a flat map, but this is not a sequence. This is an option. The really cool part about options is they can be treated as sequences through an implicit conversion. So here we're using flat map with concatenated pan digital. And if we just ran this, this would give us all of the pan digital that you can, pan digital numbers, 1 to 9 pan digital numbers you can find with the base from 1 to 999. 9999. I forgot the last 9 right there. Okay, and we can see here actually we are getting all of these different vectors. So now we're able to get all of the pan digital numbers, because what flatMap is doing is if the option is defined, then it treats it as if it's a sequence with that one value, and if it's none, it's as if this is an empty sequence. But when we're finding the maximum value, we want to find the maximum value based on the integer version of this string. So what we can do is we can take our option and we can map it. So now we're really using normal Scala collection methods with an option. So if I want to convert it to an integer, I just take each value and it'll call this function if it's defined. Otherwise, this will return none if this was already none. Now I flat map them, so now I'm going to get all of the integer versions of these. Now I just do .max. I can run this. This is going to give us our largest pan digital, and we get our answer. So that's it for problem number 38. I'll see you next time when we solve problem 39.